All right, so this is the first of two videos on galvanic cells. We're going to talk about the components and how to find the voltage of a galvanic cell, and then we're going to look at some applications with galvanic cells. Galvanic cells are your batteries. They are reactions that are going to occur spontaneously. There is some sort of interface, in this case, a wire, that is used to move the electrons between the reducing agent, with the substance containing the element being oxidized, and the oxidizing agent, the substance that contains the element that's undergoing reduction. That energy, the electrons that are being taken up through that wire, can then be used to generate a current, which can be used to perform work. And it will do that over periods of time. So, in a galvanic cell, you will have your oxidizing agent separate from your reducing agent. They'll be their own components. You will have some sort of salt bridge or porous disk that allows ions to move between the two sides. Those ions are not what are in the galvanic cell components to begin with. They are ions that will not react with either the anode or the cathode, something that like sodium nitrate. And what they do is, because you're having the two half reactions occur between the anode and the cathode, with the anode side, you're going to be producing a lot of positive ions. With the cathode side, you're going to be reducing your positive ions. So we need to balance out the charge, because if the charge difference between the two sides becomes too extreme, it will make it so that the reaction is very difficult to continue, because your compartments are going to have that charge in there and they're not going to want to generate any more ions or lose any more ions. So by adding ions that will help to maintain the charge but do not interact with the components of your two parts of your cell, your anode and cathode, we're able to keep that charge in each compartment zero. So that's an example of a salt bridge. Notice the salt bridge is between the two components or two compartments in the solutions. All right, the wire connects the anode and the cathode, the metals, but the compartments are connected to one another through that salt bridge in terms of keeping that charge neutral. If it's not a salt bridge, it would be some sort of porous disk, which you can see in part B. So the electrochemical reactions are going to occur where the electrodes are actually interacting with the solution. And I'm going to show you some pictures to help you visualize this a little bit more. That's where we actually have the electrons being lost or gained. I talked about anode and cathode previously. Your anode is the site of oxidation, and your cathode is the site of reduction. And your electrons will always move from the negative compartment, the anode, to the positive compartment, the cathode. Why do we refer to the anode being negative? Well, the anode's losing electrons, so it's giving up those negative electrons while the cathode is taking them on. And so because it's taking them on, it's going to become more positive. The anode and cathode do not have to be left to right. They can be right to left. It really doesn't matter. But the electrons will always flow from anode to cathode. The electrons will always get lost before they are gained. And so this is just a reaction between zinc and hydrogen ions. Typically, when you have a electrochemical cell that is galvanic, you'll have two metals acting as your electrodes. If one of the half reactions does not contain a metal, like it in the case of hydrogen, we have to put some sort of inert metal in there as the electrode. And in this particular example, they're using platinum, which isn't going to react with the hydrogen ions or the chlorine ions. It's not going to have any impact on the reaction itself, but it allows for the electrons to be transferred and to be moved from the anode compartment to the cathode compartment. Okay, so I told you I'd show you a little bit more of a visual as to what's actually taking place. We said at the anode, we're losing electrons. So the zinc metal, by giving up the electrons, is going to produce more zinc ions. The zinc ions are positively charged, which is why we have the anions moving from the salt bridge or the porous disk into the anode compartment to neutralize that increase in positivity. Over in the cathode side, we're gaining those electrons, and as we gain those electrons, the copper ions become part of copper metal. So we're giving up positive ions, and as a result of giving up the positive ions, remember the cathode is the positive compartment, the anode is the negative compartment, we need to add cations to that cathode compartment to balance out the copper ions that have been converted into copper metal. So you would see how the anode electrode is going to reduce its mass because you're going to be losing some of the zinc atoms to be forming zinc ions, while the cathode compartment, the copper metal in this particular electrode, is going to be gaining mass as it produces more copper atoms from the copper ions that are floating in solution. Another thing that I neglected to talk about, I'm sorry. Within your anode and within your cathode, you have your metal electrodes. The solution again is in there so that you're able to convert the metal atoms into metal ions or to take the metal ions and form metal atoms out of them. Um, so you have to have the both sides of the half reaction have to be present in the compartments for the electrochemical cell to be able to move forward. In a standard electrochemical cell, one at 25 degrees and a pressure equivalent to 1 atmosphere, you would have pure metals and you would have solutions that are 1 molar. So we're going to practice one of these, and I don't know why I didn't animate the reaction side, sorry. We're going to sketch a galvanic cell for this reaction. We've got copper and silver ions making copper ions and silver. We're going to show the electron moving, the electron flow. We're going to show how the ions are migrating through the salt bridge, and we're going to identify your cathode and your anode. You're allowed to assume the reactions are 1 molar, and I've given you the balanced reaction. Sorry about that again. Remember the first video I reviewed with you how you would go through and balance these half reactions? If we look here at this reaction, we see that copper is forming copper 2 plus. So the copper 2 plus is going to be gaining 2 electrons so that's going to be going through the reduction, while the silver ion, the copper is giving up 2 electrons. So the copper is undergoing oxidation. The silver is gaining 1 electron to become silver atoms. So the silver is undergoing reduction, the silver ions. Because silver is gaining 1 electron and copper is losing 2 electrons. When we balance this, we needed the 2 silvers on both sides of the equation. Blah. Sorry about that. I'm going to show you a little bit easier way to be able to do the half reactions in a couple of slides, but we'll start with this for now. So you see how I have the 2 compartments. I have my anode and cathode. I have my salt bridge connecting the 2 compartments together. We talked about above how copper is being oxidized. So that's going to be your brownish rectangle. And silver is undergoing reduction. So that would be your silvery rectangle. So my anode is on the left and my cathode is on the right. Again, my anode has a negative charge. My cathode would be have a positive charge initially until that salt bridge gets working. We want to show our metals and our solution surrounding them. If you want to label those with 1 molar, you're welcome to, but since I told you it was 1 molar, you don't really have to. We know that the electrons are going to move again from anode to cathode. Okay. I'm trying to see if there's anything. Oh, we've got ions to put in here. So our ions are going to move, and they're not moving from the cathode to the anode. They're moving through the salt bridge that's flowing between them. So the anions are going to move into the anode compartment, and the cations are going to move into the cathode department. And again, the salt bridge is the more circular shape that's connecting the two. So they both have cations and anions in that salt bridge that could disperse into your anode and cathode department, but you're going to see a greater shift of anions over to the anode to balance out that increase in positive copper ions that are being generated. And you're going to see a net increase in cations from the salt bridge flow over to the cathode compartment, to balance out the silver ions that have been lost. We can also show galvanic cells using a line notation format. When we do this, we basically are just showing the net changes that are taking place between the anode and the cathode. Anode components are always listed on the left side, and cathode components are on the right side. We represent the pure substance, the solids, and the solutions by a single line. That's how the phase difference line is being represented. Um, and we write them just as we would in our half reactions with the reactants on the left side of the vertical line and the products on the right side. We separate the two compartments, the anode and cathode, from one another with a double vertical line. And as I said previously, I'm not going to ask y'all to do anything with this. If for some reason you had a reaction that did not contain a metal, we would represent that in the line notation with whatever the conductors we're using. In the example I showed you earlier, it was platinum, but it could be other metals that are chemically extremely unlikely to react with the components making up your particular chemical equation. So I'm going to do one for you right now, and then I will let you practice one. This one is not in your notes. This was just here to give you an example of what one would look like. A galvanic cell is based on the following reaction. We've got it between iron and sodium. We see that iron is becoming less positive because it's gaining electrons, so iron is being reduced. Sodium is becoming more positive, so we see sodium is being oxidized. In the line notation format, sodium being oxidized would be found on the far left, and it would turn into, so there's your two half reactions. Sodium would be on the far left because it's undergoing oxidation, and then we have the single line separating it from the sodium ions, reactants from products, the double arrow, or sorry, the double line separating the anode compartment from the cathode compartment. With reduction, we have the iron ions that are being transformed into iron atoms. And so we see that those two components are separated by a single line. You do not have to include the S's or the AQs, but you do need to make sure that you distinguish between the ion form and the atom form, and that you do have them in the correct order. That for oxidation, and for reduction, they always are going to be written reactants on the left side of the single line and products on the right side. And that the oxidation will always be written before the reduction, and the two will be separated with the double lines. So if we go back to the reaction that we just labeled with that galvanic cell, we saw in that galvanic cell how the copper was undergoing oxidation and that the silver was undergoing reduction. So on the left side of our double line, we would have the copper, and on the right side of our double line, we would have the silver. The copper would be written with a single line before the copper 2 plus. Then we would have our double lines. We would see our silver ions, a single line, and then the silver atoms. So again, reactants to products for both half reactions, oxidation, the anode components before the cathode components. How these galvanic cells are going to play a role in your everyday life is that we see them in batteries. You have batteries that can be both primary and secondary. Primary batteries are the ones that are one use only that we tend to get for old school, fill in your calculators or for flashlights. Secondary are what we see with our cars, our phones, our Chromebooks, everything that we basically use that we don't have to continuously go through batteries. This will be the last part of the video for this first part with galvanic cells. I talked earlier about how electrons move from the anode to the cathode, and that the electrons are going to be able to be harnessed, and that what we are generating is an electromotive force. It's basically what's pulling the electrons to move from one side to another. That potential energy change can be represented in terms of charge, and we call that term E cell, and its units are volts, a joule per coulomb. Sorry. And we can relate coulombs to current because coulombs represent the amount of charge that's going to pass through an electrical circuit when we have an ampere that has flown for 1 second. So in your packets, both your note packets and in your homework packets, I have put this table that is also in your textbook that relates reduction potentials for different substances. So if you notice on this table, a lot of the half reactions are already written for you. They're already balanced. So there's not many that you may actually have to go through and balance, which is, so I hope that that will help some with the stress. These are reduction half reactions because we always see the electrons on the left side of the arrow. If we wanted the oxidation half reaction, we would take the reduction half reaction and flip it. So in the case of the first reduction half reaction, if I wanted the oxidation half reaction, it would be 2F minus yields F2 and 2 electrons. When we do something like that, we do have to switch the sign for the voltage. It would become negative 2.87. And it would work that way for any of the other half reactions. The way this chart is set up, the stronger reduction or stronger substances that are capable of going through reduction are listed at the top, and the substances that are less likely to go through reduction are listed at the bottom. So lithium would be one of the strongest to be oxidized, while F minus would be one of the weakest to be oxidized. This extra one down here was for the lab that I normally do with this, so please don't get too stressed out about that being there. That's why it's not fitting in. I needed it for your lab. Okay. Again, that is in your note packet. It is in your textbook. It is in your assignment packet. So definitely look at that for a reference. All the half reactions potentials are based on hydrogen's potential, SHE, which has a voltage of 0. Now, these E signs to represent our voltage have this degree next to it, and the degree is what we've talked about previously with delta H and delta S and delta G. It's at 25 degrees Celsius and pressures of 1 atmosphere, concentrations of 1 molar pure substances. If you have a larger, more positive voltage as a reduction half reaction, you would be a more effective oxidizing agent because you are more willing to gain electrons. If you have a smaller reduction potential and more negative reduction potential, you are more likely to be a reducing agent and to be a pretty strong reducing agent at that. You are more likely to lose your electrons and undergo oxidation. So there are two reduction potential examples. Um, we see the voltage versus the SHE. I'm not going to be writing the versus SHE after this. But when we combine our reduction and our oxidation half reactions in a galvanic cell, the two voltages should give us, when combined together, a positive overall voltage for the cell to be a galvanic cell, for it to occur spontaneously. So as I said previously, you always will have an oxidation half reaction and a reduction half reaction in a galvanic cell, and that when you combine their individual cell potentials with one another, the one that's oxidized would have its sign reversed, and we would just add those two together. These potentials are intensive properties. They are not dependent on the amount of material that we have present. And that's a little bit different than what we talked about with just joules on its own. So because these are intensive properties, when we write those balanced equations between the half reactions, if we have to multiply the reaction by a coefficient to get the numbers of electrons balanced, the cell potentials do not change. And you'll see that in our next example. For a reaction to be spontaneous, for it to be a galvanic cell, it's got to have a positive cell potential. So I've got copper and silver ions. You're seeing this example a lot. I tried to use this one to work through all the different applications so you could kind of follow it through. I would go to that chart that I just showed you and find the cell potentials for these two half reactions. So if I go look on my chart for copper, I see that copper is able to generate a voltage of 0.337 volts when it's written as a reduction half reaction. I need copper to be written as an oxidation half reaction, so I flipped it. And when I flipped it, the sign became negative. Silver is going to be reduced, so it would just be writing its cell potential as it was on the chart, 0.799. Again, when I want to find the cell potential overall of a chemical reaction, it does not matter if the number of electrons required a coefficient to be multiplied by to get the electrons to balance between both sides. Okay? Why did I flip that one? Sorry, I think I was using the chart in my old textbook. Okay. You would not have had to flip the silver one based on the chart you have. You would have had to flip your copper one. And so you see when I flipped the silver one, it went from negative 0.799 to 0.799. My guess is on our chart, you would still see it as 0.799, and the copper one you would see initially is 0.337, and then we would flip the sign. Adding these two together, we get that the overall voltage is 0.462. Notice that again, when I multiplied silver by 2 to write that balanced equation, I didn't change my cell voltage by a factor. All I can do with the cell potentials, because they're intensive properties, is to change their sign. If I flip the half reaction, the sign flips. So when I added these two together, I got that they do have a positive cell potential. So this particular reaction is spontaneous, going from the reactants to the products as it is written. We can look at that chart to be able to examine what substances, what ions or elements are able to act as more effective oxidizing agents and as more effective reducing agents. So on your chart, I went through and looked at all of these different substances. I'm just going to write them down for you. I went and found each of these. If you go look on your chart for that table 20.1, you would see all 7 of these reduction half reactions. Because we want to order them based on their strength as oxidizing agents, we know that these are all being written as reductions, and that's what oxidizing agent is. So the more positive that cell potential, the more effective it is as an oxidizing agent. So I want to order these basically from biggest to smallest or from smallest to biggest. I went from smallest to biggest since I wanted to do it based on increasing. So the most negative was the magnesium ion. The next most negative was water. The third most negative was the nickel. And then our transition point, I think our first one that's the least positive is going to be the silver. Then we're going to move on to nitrate, the dichromate, and the chlorine. So when I list these in order, from smallest to largest in terms of being an effective oxidizing agent, magnesium would have been the least effective and chlorine would have been the most effective. You can put commas, I don't care, but you need to show me what your order would be. I can do this for oxidizing, and I can also do this for, I believe this one is supposed to be reducing. Sorry, I put oxidizing there. So I went through again to the chart and found the different substances. And this time I want to have them, if I'm pretty sure your notes say reducing. Yep, your notes say reducing, and I did do it as a reduction. I just didn't word it right. So if I want to look at them as increasing strength of reducing, if you look at the reactions that I've written, I went ahead and flipped them. I made them become oxidation half reactions since that's the process that we're looking at. So all of these have signs that are the opposite of what's on your chart. So the one that is going to be the most effective as a reducing agent would be the one that is most positive, and the one that is least effective would be the most negative. So the most negative one was the Mn2 plus, and then I move on to chlorine ions, chromium 3 ions, and I have one more negative, the hydroxide ions at the bottom. Hydrogen's going to switch over to the positive side, then we'll move on to nickel, and then we'll move on to aluminum. So in order from least effective as a reducing agent to most effective as a reducing agent would be the manganese ions all the way up to the aluminum atoms. One last thing that I could ask you about with this particular type of question is to determine whether a substance is capable of reducing or oxidizing another substance. So in part A, I asked you, is tin capable of reducing iron ions? If tin is capable of reducing the iron ions, then we want to look at tin as it's undergoing oxidation. That would be the cell potential for iron ions being reduced, and again, this is on your chart, to iron atoms. If I look on your chart and I find a half reaction for tin, I want to write that as an oxidation. So I would flip it, and when I do that, I would change the sign of that particular half reaction cell potential. These two added together give me a negative voltage, so the tin would not be capable of turning iron ions into iron atoms. If I look at it in terms of whether it's able to reduce bromine, I would still have that tin half reaction, but now I would have to look at bromine's reduction half reaction. I see its cell potential is 1.08. 10 again is going to be flipped. It's still 0.14. And when those two are added together, they would give you a positive cell potential. So although tin is not able to reduce iron ions, it is able to reduce bromine. I can look at this for reducing, and I can also look at this for oxidizing. No matter which way I'm looking at it, I have to look at my chart. This time I want copper to be oxidized, so I want the zinc to be reduced. So I would find the reduction half reaction for zinc, negative 0.763 was its half reactions voltage. I want to find a half reaction for copper and then flip it to show it undergoing oxidation. So that's the copper half reaction. Those two added together are going to give a very negative cell potential, so that would not be possible under these conditions. If I look at it for magnesium, again, zinc's half reaction is not going to change. I want to find magnesium and flip the reaction to show it going through oxidation, although I don't know why I put 10 there, but I'm pretty sure that's magnesium. I'm looking. Yep, that's the right cell potential. Assume 10 is Mg and 10 2 plus is Mg 2 plus. When I add those two together, I do get a positive cell potential. So that particular half reaction is capable of happening.